Why?
Conversation. This is the function f of x equals 4 minus x squared. Okay? And our task as a group is to come up with a method besides integrating, because that's a spoiler. We're leading to that. So Riemann sums are to integration as limits are to derivatives. Okay? We're going to have to go through this process of understanding exactly what's happening before I'm going to let you just jump straight into integration. Okay? This is kind of the backup. This is the precursor. So you know some of this. You haven't deep dived into all of it. Okay? So pretend you know very little. And let's get through the fundamentals first. Okay? So I want to come up with a system for how might we find the area under this curve on the interval, and let's go from 0 to 2.
Oh yeah, can we do the thing where we come up with a bunch of little bitty shapes?
Okay, so little bitty shapes, sure. Little bitty shapes. What kinds of shapes would you like to use?
Octagons.
Rectangles. Octagons. Not helpful. We could stack them Tetris style. Okay, octagons is a no. Rectangles is a yes. How many rectangles?
We do one big one that hits the corner right there?
Okay, we could do one big one that hits the corner right here.
No, like on the inside. And so there's like area on the inside left from the, and then we can like do semicircles.
Triangles. Oh.
Okay, I'm confused.
Starting at like 2 dashes,
Like inside.
and then like the inside, and it hits like, no.
Go up there. Go up
Oh, yeah,
two
go
on the
in.
y-axis.
So like if we do like bang, bang, and then we can do like a semicircle for the rest of it.
Oh, so okay, but here's the rule. We have to use the same shape the whole time.
So just do a bunch of little teeny
Don't
tiny
deck-
rectangles.
Okay.
So we can do a whole bunch of little teeny tiny rectangles. Okay, well, let's first get some skill set here. Let's find the area under this curve only using 2 rectangles. I'm only going to allow you to use 2. These may be called partitions.
Are they equally sized?
No.
Great question. Are they equally sized? Let's let them be equally sized.
So then basically just one.
Well, that's
Like they're equally.
So if I let them not be equally sized as far as their height is concerned,
Area.
but let's do equally sized as far as their width is concerned. Okay, so can you compute?
Yeah, it's going to be a bit lower than like 3.
So the actual area is going to be a little bit lower. Okay.
Somewhere below.
How do you know it's a little bit lower?
It goes out.
Because it feels like my rectangles are more than the actual area, right? Okay. So, but let's find the area of these 2 rectangles. How would you do that?
1 times 4.
So length times width. How do you know how high it is?
Because the dash marks.
Oh, you go on the y-axis. Okay. So the width of this rectangle, this width right here, might be 1. Okay. How did you know it was 1 besides the fact that I wrote 1? How else could we have found that? Okay, take the x-axis. So it's 1 mark, right? Because I split it into 2 rectangles. But what if I had done into 4 rectangles? How would you know how wide they are? How?
Dividing 1 by 2.
Dividing 2 by
4. Or 1 by
2 by 4. Dividing 2 by, what if I made 16 rectangles?
2 by 16.
Okay, so let's come up with a formula for the width. How do I tell how wide the rectangle is? And we'll call that delta x.
By total by number of rectangles.
Total meaning how far? How do we get total?
X-intercept.
Okay, could be on this function, x-intercept. What about on any function? On an interval from A to B.
Domain.
On an interval from A to B. Yeah, domain. So I'm going to take the interval from A to B, and I'm going to find the difference, B minus A. So if I'm going from 0 to 2 here, the difference is going to be 2 minus 0. That tells me how wide of an area am I talking about here. And then I'm going to divide that by n. N being what?
The number of
Number of rectangles. Okay, so B minus A over N, that's going to tell me how wide each rectangle is, its width. Do you agree with that? Okay. And then the next question is how high? How high is the rectangle? How tall is it? And how would I tell that?
Depends on because the graph changes constantly at height.
Okay, so the graph changes constantly with its height. Gosh, y'all are way up there. So if the graph is changing constantly with its height, how might I be able to tell what my height of the rectangle is? What could I do? How do I get that number?
Is it like a mathematical thing or like a
Yeah.
looking at the graph thing?
Yes, both. How do I tell? It's an input-output type thing.
We can just count. Oh, we can't do. Do you want to do it like manually or like an equation to do it?
You have to have the equation, right? So how would I tell how high the rectangle is at that certain point? I might have to plug in that number. You with me? Mm-hmm. Okay. All right. So kind of starting to turn the wheels here. Okay. So now open your packet.
The height is like f of.
F of something, isn't it? Okay. So let's open our packet. And so you've got a toolkit here. On this front page, it says to find the area of f of x on the interval from a to b using a right-hand Riemann sum. And we'll come into later what is the difference in a right-hand Riemann sum, what is the difference in a left-hand. I will tell you that the right-hand Riemann sum means that my corners of my rectangles touch on the right.
Could be an underestimate.
Could be an underestimate depending on the function.
If it's concave down.
If it's concave down, it's an underestimate. If it's concave up, a right-hand Riemann sum is going to be a little bit above the curve. We did talk about this. Good.
And then what are like the center one?
Yeah, I was like, never heard this before. Have we talked about this before in your class in calculus? Okay. Yes.
I like the middle where it goes through the middle of the top of the rectangle.
The middle, so that's called a midpoint sum.
I like that one.
So that's where we're headed this week, or in these two lessons. Okay? But in order to calculate a right-hand Riemann sum, we need a toolkit. Okay? The first thing we've got to find is the width of each rectangle. That is determined by taking the interval from A to B. So you're going to find the difference. B minus A tells me how wide of an area am I talking about. Divided by N, total number of rectangles.
Do we just get to choose that number?
So really, if we're actually wanting to be super accurate, what do we do with N?
The smallest number we can, or the biggest number we can.
We take it to infinity. So it's a limit as N approaches infinity. So as the number of rectangles increases. I also told you that you could consider as delta x the width of the rectangle if I take that to 0. Same idea. I can either take the width of each rectangle down to like a hairline, or I could take the number of each rectangle to infinity, which does the same exact thing. I'm getting really, really small rectangles. Okay? All right. The next thing we have to consider is where is each rectangle's location. So that's each step on the interval. So once we know how big we want them, but then that's different depending on if I'm talking about this rectangle or let's let this one be rectangle number 2 or this one number 3. Depending on which rectangle I'm actually talking about, it's going to have a different height. Are you with me? They all have the same width, but each rectangle's f of whatever is going to be different. So I need to know what rectangle am I referring to. Each step on the interval is going to be found by using x sub k, where we start at A being the first number on your interval. We start at A, and then we hop out delta x times k. So if I'm talking about the third rectangle here, I'm talking about 3 away at a distance of delta x apiece from my starting value A. Everybody hear that? Do we understand? So delta x is the width of each particular rectangle. Delta x, that's this distance right here. If I'm talking about the third rectangle, then I want to be 3 times delta x away from my starting value at A.
How do we calculate that if we want it to be infinitely small, like the width of the rectangle?
We'll get there. Okay. The next thing that I have to consider is then what is the height of each rectangle? And this is the input-output thing. So depending on which particular rectangle I'm talking about, that's this x sub k business. Then I input that into the function, and I will know the height of that rectangle at that place. Okay, that's f of x sub k. Now, how do I find area of a rectangle? Length times width, base times height. What's the base? The base is going to be delta x. That's its width. And its height is going to be f of x sub k. And the x sub k allows me to find the different heights based on the different locations of the rectangles where they hit the function. Okay? And so then, once we find each individual area of each individual rectangle, we add them all up. That's the sum, right? That's the Greek symbol. It means add them all up. So you're going to find each individual area's height, or each individual rectangle's area. And then you add them all up. And this gets to be more and more and more accurate if you'll take the limit of the sum as the number of rectangles goes to infinity. Right? And so that's the adding up of this. You with me? Now, that looks real chunky and real clunky. So in order to smooth it out and make it look a little bit prettier, we see the actual integral notation, which says take the integral on a to b of f of x times dx, the distance of each rectangle. This is height times base. It's the exact same thing. Okay? Once you've learned to integrate, you kind of never look back at Riemann sums. But we have to go through this computing the Riemann sum first. What really we need to be able to do is go between the two formulas. So this is called limit notation, the one with the limit and the epsilon, or the sigma. And the other one is called integral notation. We need to be able to slide flawlessly between the two. That's the calculus task. In physics, they're like, who cares? Here's how you do it, right? In calculus, they want us to be able to recognize a limit notation versus recognizing an integral notation, and how do we say the same thing in two different ways. So we're going to dive in first to this formula, or this problem that we started today with. And this formula, or this problem, f of x equals 4 minus x squared, this is not this picture. Okay, they're not in the same picture. This actually is the picture that I drew on the first slide. So, to find the area of f of x equals 4 minus x squared on 0 to 2, on the interval from 0 to 2, your width of each rectangle is going to be delta x equals b minus a, so 2 minus 0, over n being the number of rectangles. Are y'all with me? That's the width. Each step on the interval, x sub k, is equal to a, and I would write this down so you're able to handle this. X sub k is equal to a plus delta x times k. That's going to be the same every time. So on this particular problem, what's my a value? Where do I start? 0. So x sub k is going to equal 0 plus delta x was 2 over n times k being whichever rectangle I'm talking about. If I'm talking about the third rectangle, that's going to be a 3. Okay. So x sub k is 2k over n. Now, the height of each rectangle is going to be, using that x sub k business, it's going to be f of 2k over n. And what was my function? 4 minus x squared. So it's going to be 4 minus 2k over n squared. That's how I find the height of each rectangle. Yeah? Well, how do I find the area of each rectangle? I take the height times the base, which was that 2 over n, the width. So we have 4 minus 2 over n, or 2k over n squared, times, so this is my f of x sub k, times delta x. You seeing where that's coming from? So how do I find the actual approximation of the area? That's the sum. That's the sum. That says I take all of them and add them up. From k equals 1 to infinity. From the first rectangle to n. Where k equals 1 means that I'm starting here on the right side. If k equaled 0, I would bump back and it would be a left-hand Riemann sum. Okay? Do you understand?
Sure.
And it'd be like 1/2. Would it be 1/2 in the middle?
Okay.
Where did the 4 come from?
The 4 came from the function. It was 4 minus x squared. So when we found f of x sub k, we went to our function. Our function was 4 minus x squared. And instead of x, we're putting in x sub k, which was that 2k over n.
You said in the middle it's 1/2. What does it mean?
In the middle, so for a midpoint sum, it would be it'd be an average. Let's not have that talk today.
Okay.
We'll have that talk on Tuesday.
Okay.
Yeah. Okay? So that's what we're seeing here is the final limit notation is equal to the integral on a to b of the function times delta x. She loves. Okay, so let's go on to the next page. The next page has some practice problems here.
Fine.
These are actual multiple choice AP questions. Okay. So number 1, it says choose the integral that is the limit of this Riemann sum. So which of these integrals match that limit? Okay, so here's how I kind of go about it. First thing I want to do is find my delta x. And it feels like this 3 over n is equal to delta x, 3 over n. What that means is that's b minus a over n. So b minus a must equal 3. So either I'm looking at the interval from 0 to 3 or 2 to 5 could be an option, right? Both of those have a difference of 3. B minus a is 3. So then I go to this particular piece of information. This has 3k over n plus 2, and that all is getting squared. The 3k over n plus 2, that is my x sub k, which means they started at 2. 2 plus 3k over n, because that 3 over n, that 3k over n, that was delta x. Delta x times k. So the 2 is an additional 2. That means that a must be 2. Are you seeing that? So if a is 2,
On an interval of 2 to something.
2 to something,
So is that 5 and this?
2 to 5 must be 3. So that rules out B and D. Can't be B or D because I had an initial value of A at 2. And now, if you look outside of that, let this just be, this is X now. What's happening to X?
Getting squared.
It's getting squared. So it's got to be C.
That's not. What is the x? What did you say?
Well, I've now deduced this down to being something is happening to X. X is getting squared. F of X equals something squared. So I took this X sub K business. That's this 2 plus 3K over N. And now I'm just calling that X. Instead of letting it be F of X sub K, let's just back up and let it be F of X. And so then I kind of open my eyes a little bit and I see what's happening to that piece of information. It's getting squared. So my function initially must have been x squared. Okay. Okay. So now let's look at the second one. It says choose the Riemann sum whose limit is this integral from 1 to, is that a 5? Okay, so from 1 to 5. So toolkit wise, first thing I'm going to do is find delta x. If I'm going on the interval from 1 to 5, then my delta x is going to be b minus a over n, 5 minus 1 over n, which is 4 over n. Okay, so it can't be b or d. Okay. Now let's talk x sub k. X sub k has to be a plus delta x times k. What's a in this problem? 1. So 1 plus 4k over n. That's x sub k. And what is f of x sub k going to look like? What's f of x? X cubed. So f of x sub k is going to be that stuff cubed. And I'm going to multiply f of x sub k times delta x in my sum. So C. What happened with A?
It didn't have a 4.
They lost the 4 on the K. Yeah? Okay. Let's try number 3. Number 3, it says, choose the Riemann sum whose limit is the integral from 0 to pi of sine of 3x. So my delta x piece of information is going to be what? B minus a over n. So pi minus 0 over n, or pi over n. And what's a? 0. So my x sub k is going to be 0 plus delta x k, or pi k over n. That's x sub k. What is f of x sub k? That means I'm going to take my function sine of 3x, and instead of x, I'm going to put in pi k over n. So f of x sub k is going to be sine of 3 times, sine of 3 times pi k over n times delta x, which is pi over n.
Yeah.
So are we coming up with an answer here that we think works?
Not A or B.
Okay, not A or B. D. What happened in C? They lost the pi. Yeah?
Yeah.
Okay. So I think you guys do 4. We're not going to do 5. Okay, I'll do 4 with you. We're not going to do 5. Okay, 5 is more information than I feel like we need. Also, I'm going to let you skip the next page in your packet. So it's got more multiple choice. So flip over to, skip the next 2 pages, those multiple choice questions. I'm not interested. The next thing we're going to look at is the circuit that's called writing and interpreting Riemann sums. So you should be able to get going on this circuit over the weekend based on this information, and only this one. Okay? Let's do the next question, and then we'll start the circuit. Is that good with y'all? Okay. So number 4, it says choose the integral that is the limit of the Riemann sum, and you've got this big honkin' Riemann sum. Where do you want to start? Find the delta x.
3 over 10.
So delta x in this problem seems to be 3 over n. which means my interval b minus a must have been 3. Okay, all of those have that. Okay, so let's see if we can find our x sub k. Let's see if we can come up with that information. Feels like that's going to be what?
Well, A is 2.
Feels like a might be 2. Do y'all agree with that? Okay. Feels like a might be 2. Okay, here's my issue with this. That 2 is not outside of the function. That 2 is inside the argument.
I thought they evolved it inside the argument.
What?
So that number 2, when we said 1 was A, it was also
Right.
isn't it?
Yes. This is where we can't tell if it's B or C. The right answer here is B. So it is B. It feels like it should be C. Right?
Yeah.
Yeah. It feels like we should be multiplying 2, so we got to figure out why that's not the right answer. Give me a second. I know that they're multiplying by 2 because we went from 3k over n to 6, right? What's the difference in the 2?
B and C have different intervals,
Yeah.
and they have one.
Right, B and C, but I could justify that C works, right? Because the difference is 3. How do I know that I'm starting at 0 and I'm not starting at 2? I think on this one they both work. I can't remember what's the reasoning for this. I think this is when Damien shut his book and was like, okay, and I'm done. I don't care anything about this. It has to do with the location, and I'm just not seeing the difference right now. I told y'all, grace upon grace upon grace. Y'all just be... Ugh. Okay, I'm going to get back to you on 4. I understand that I know that it's down to B and C, but there's some nuance, and I'm not remembering why those are different. So we're going to pause on that, and I'll clear that up on Tuesday for sure. But let's go ahead and jump into the circuit because I don't want to waste any more time on these questions without actually letting you practice some things. Is that fair? Okay. Sorry, y'all. Gosh, I just can't remember. Why do I know? I don't know. I'm going to move on. Okay, so we're looking at number 1 on this circuit, and it says find a limit equal to 0, the integral from 0 to 4 of x squared plus 1 dx. And so you start off with your delta x, which is going to be 4 minus 0 over n, or 4 over n. Your delta x your x sub k, which tells me which rectangle I'm talking about, right? What's a?
0, 0.
So 0 plus 4 over n times k, or 4k over n. F of x sub k is going to be this function with that x sub k in place of x.
Yeah, so x, 4k over n in place of x, so 4k over n squared plus 1.
Plus 1. So now when we write our limit, this is going to be the limit as n approaches infinity from the first rectangle to the nth rectangle. That's this notation. Of, and it's always f of x sub k times delta x. So 4k over n squared plus 1 times delta x, which is 4 over n. And because they're nasty, they went ahead and squared the 4k over n. So when you find your matching answer, they called it 16k squared over n squared plus 1 times 4 over n. There's some trickery that they did on a couple of these.
So she's not our friend.
This is Mark. Mark is not our friend. Mark is not our friend today. Okay.
And that's the bottom left on the next page?
Yeah, on page 5. Bottom, whoa,
No, I just saw 16. There's a lot of those actually.
yeah. Page 5, bottom right. What'd you find? The number 5 in the bottom of the page.
Oh, I see. I counted 5 pages.
Sorry.
It'll work out.
Okay, so the second one, number 2, it has find a limit equal to the integral from 0 to pi over 2 of cosine 2x dx. Cosine of 2x dx. So delta x, I called it pi over 2n. Because it's pi over 2 over n. And a is 0. So my x sub k is going to be 0 plus pi k over 2n. Pi over 2n times k. F of x sub k is going to be cosine of 2 times pi k over 2n. So what happens with those 2's? They cancel, which is going to equal cosine of pi k over n. And so when I find my limit business, I'm looking for the limit as n goes to infinity of the summation of rectangles from the first one to the nth one of cosine pi k over n times pi over 2n. Okay. Is that enough to get y'all going?
I think so,
I think so.
Think so? Work together. Work together. Don't try to go this one alone.
I think I found it, maybe. Yeah.
All right. We'll do the rest of this lesson. So the table stuff, the rest of this packet, we'll try to come in on Tuesday and hammer out. So you've got a while between now and Tuesday to work on this. I'll take mine home this weekend. If you butt a stump and you need help, holler at me.